Welcome, everyone, to the elusive nature of intersecting paths on a grid. I'm Marty Golumbic, and I'm very happy to welcome all of you here in the classroom and those of you in cyberspace. So let's go to the slides. In today's lecture, we will be talking about work that has been going on for the last 12 years approximately. We'll talk about the family of B EPG graphs and the family of boundary-generated EPG graphs and approximation algorithms for them. Joint work with my colleagues, Marina Lipstein, Michal Stern, Gila Morgenstern, Deepak Rajaprasad, Dror Epstein, and Gila Morgenstern again. So, as many of you know, my interests in algorithmic graph theory have spanned 4 decades, with a special focus on structured families of graphs and various types of intersection graphs. And one of those applications of these concepts is the topic of paths on a host graph. Specifically, today we're going to be talking about paths on grids. Paths on grids are everywhere, as you can see from this slide. It could be from the puzzles where you are counting the number of ways that you can get from the northwest corner to the southeast corner. It might be games such as you have on the right. It might be a network of subways or buses that is pretty much close to a grid. Or it could be from electrical circuits, as we see in the lower right-hand corner. Now, the interaction between pairs of paths can be seen in sort of 2 ways. The paths on the grid, as I've shown in this diagram, cross in different ways. There is the vertex intersection type and the edge intersection type. Here, the arrows are pointing to paths that share a common vertex only, a grid point. These arrows, however, show where 2 paths actually share an edge of the grid. That's the major difference between vertex intersection versus edge intersection. In this talk, we'll be talking about edge intersection of graphs. Now, the edge intersection of graphs of paths on a grid is defined formally here. For every vertex, there corresponds a path such that xy is an edge in my graph if and only if the path of x and the path of y share at least one grid edge. So in our example, here I've circled green overlapping with brown, and that forms an edge in my graph. On the other hand, here, yellow and green intersect only on a single grid point. So they do not edge intersect. So on my graph, I do not connect those 2 nodes. Now, the motivation for our looking at this is sometimes given from problems in circuit design. Here you can see a VLSI layout problem that needs to place these paths on a grid. And crossing is not so much of a problem. You can build a little bridge over it. But sharing a grid edge would be a bigger problem. Now, especially the students who are here that have taken my course know that a lot of things started with the study of interval graphs. And the interval graphs, which are the intersection graphs of paths on a straight line, intervals on a line, gave birth to the family of chordal graphs and the family of circular arc graphs by generalizing, putting those strings around a circle, and the AT-free graphs. Those were classes of graphs that were investigated during the 1970s. The second generation we introduced EPT graphs in the 1980s and interval tolerance graphs in the 1980s. And EPG graphs, that we talk about today, were introduced only about 2005. So they are perhaps even a third generation. The first EPG graph results from the early years when we first started studying them started with this theorem. Every graph is an EPG graph, and every graph has a representation on a grid of n by 2n size, where n is the number of vertices. Moreover, every graph has a monotone EPG representation, where the paths are monotone, on an n by n plus e grid. Okay, let's get those slides back. You could ask, is an n by n grid always needed? And that was answered a couple years later by Andrew and Andre in 2009. For any fixed degree d greater than or equal to 4, a grid size of at least n squared is needed to give a representation for every graph on n vertices with a maximum degree d and sufficiently large n. So for example, the complete graph, the complete bipartite graph on n by 2 vertices needs n squared over 4 grid edges. So you can't do better than that as a kind of minimum size grid to represent your graphs. Monotone representations look something like this. Now let's just look at this example. I would like to construct this representation on the left by just looking at the graph. The graph, I number the vertices 1 through 5, and my construction goes like this. On the rows, I number 1 through 5, according to the vertices. On the top, I list the vertices and the edges in my graph, and I list them in sort of alphabetical order. And here's how I define a path. For vertex 1, it has neighbors 5 and 3. So my path will start in row 1, go up to row 3, its first neighbor, over to the edge 1, 3, up to the next neighbor 5, over to 1, 5, and that will be its path. Similarly, if we were to look at number 2, 2 has neighbors that are 3, 4, 5. So with 2, he starts in his row, goes over to himself, goes up until his first neighbor 3, goes over to his edge 2, 3, up to 4, over to the edge 2, 4, up to row 5, and over to 2, 5. And this kind of encodes the graph in this representation. You can do this for any graph. So what's the big deal about looking at EPG graphs? Well, we need to ask a few questions of what would be interesting. First question might be, well, is a grid size on the order of n times e required to give a monotone representation for all graphs on n? I suspect the answer is yes, but no one has looked at that question yet. Now, since all graphs are EPG graphs, let's find something more interesting to do. Well, look at specific special classes of EPG graphs. And to do that, we proposed to look at restricting the number of bends that are allowed on a path. So we will call BK EPG the class of EPG graphs where a path may have at most k bends. Well, that seems like a pretty strong restriction. For example, if k was equal to 0, you couldn't bend them at all. Well, these would just be segments in the grid, horizontal segments, vertical segments. And if 2 of these segments were to share an edge, they would have to be in the same row or the same column. So the graphs that are B0 EPG are exactly the interval graphs. And each row and each column might give you a separate disjoint interval graph. Okay, so we are generalizing interval graphs in yet another way. Let's see what happens next. So bends of wire is motivated largely from the VLSI discipline, where you have wires that cross in different ways, and you want to manufacture so that there won't be so many bends, because every bend requires you to do something. So it's good in general to have not a lot of bends. A high number of such holes that you would need to create for crossing paths would increase the layout and the cost of the chip. And a lot of research is done to minimize the number of bends of a layout. That's not exactly what we are doing overall. We are looking at particular kinds of paths. And we will focus on B1 EPG, the paths that have only one bend per path. Our first theorem was that every tree is a B1 EPG graph. And here you can see a clear illustration of why that would be. Take a tree, choose a root, and create a big interval, a big L path, like I have pointed to. And now go to its children and put in smaller paths. And then go to the grandchildren and smaller paths yet. And then the great-grandchildren, and so forth. As I finish my whole descendant tree, I will have created a representation for that tree as single bend paths. Notice also they happen to be of the same shape. Now what about cliques in such graphs? Well, we have an interesting theorem here. The cliques have exactly two possible B1 EPG representations, either as an edge clique or as a claw clique. An edge clique on the left is when all the paths share a common edge. So clearly they all share a common edge. They are a clique. But there's another kind, and that is a claw clique, where paths take 2 out of the 3 legs of this claw. And so if anyone has 2 legs out of 3, every pair will, in fact, share one of those legs. So here I have a representation of the complete graph on 6 vertices. Every pair shares at least one of these claw edges. And we have a wonderful theorem that says that if P is a B1 representation of a graph, then every clique of the graph corresponds to either an edge clique or a claw clique. There are only 2 kinds of cliques. And here's a short proof of that. If there were no bends, well, we have an interval graph and we're done. But if some path P sub u bends, and it uses the legs E1 and E2, then all paths that share only E1 or E2 must share some other edge, namely some other common edge E3. And therefore, it must be a claw clique. Some consequences of that theorem allow us to show that the sun graphs, SK, where k greater than or equal to 4, are not B1 EPG. On the left, we have the 3 sun. It is B1 EPG, and here's a representation for it. And S4, which is on the right side, is not B1 EPG. Sorry. Now, Andre and Bernard Ries continued working and showed a number of other results. And one of their results was that in every B1 EPG graph on n vertices, it will either contain a clique or a stable set of size at least n to the power 1/3. It's a kind of interesting trade-off between cliques and independent sets. Now, we also study the Strong Helly property for B1 EPG graphs. What do I mean by this notion of strong Helly? Well, let me show you. First of all, single bend paths do not satisfy the usual Helly property. The usual Helly property is if every pair of items intersects, then there is a common intersection between all of them. Single bend paths don't satisfy that. Pairwise vertex intersection does not necessarily imply global vertex intersection. And here's an example. Suppose we have these three paths, P1, 2, and 3, on the grid, as shown on the left. Well, they pairwise intersect here on an edge, here on an edge, here on a vertex. But their global intersection, P1 intersect P2 intersect P3, is empty. But B1 does have a kind of strong Helly property. And here's a theorem. The first statement of the theorem says the following. Let P be a B1 EPG representation of G, and let P1 through Pm be the paths. If Pi and Pj share an edge for every pair I and j, then their intersection is non-empty. That is, pairwise edge intersection does imply global vertex intersection. Right? So if they pairwise share an edge, they can share a vertex, not necessarily an edge. An example, if our three single bend paths had pairwise non-empty edge intersection, but they didn't, two of them just intersected at a point, and if they did, then they would have a grid point in common, like they do in the claw. So the second part of the theorem is called the strong Helly number 4 property of B1 EPG graphs. That there exist 4 paths out of my collection, I, j, k, l, such that the intersection of those 4 is equal to the intersection of all of them. It's a different kind of property. It's no longer asking empty, not empty. It's actually saying that for single bend paths, I can choose 4 of you, and you form a committee, and you take your intersection, and you represent the intersection of the whole group. Moreover, if your representation happens to satisfy the usual Helly property, then the strong Helly property, strong Helly number would be 3. That is, if P satisfies the usual Helly property, then there exists 3 paths. I only need a committee of 3 people whose intersection gives me the intersection of the whole group. Well, that's what we know about cliques and strong Helly. Now let's look at chordless cycles. What could chordless cycles look like in an EPG graph? Well, here are 2 ways that you could represent them with single bends. You could have what is called a true pi. These 4 paths go in and out, in and out, in and out, in and out. And you see that you get the chordless cycle. Opposite paths only share a vertex, so they are not adjacent in the graph. I could also have it represented like this, a false pi. I'm still cutting the pi into 4 pieces, but I'm cutting them slightly differently. A bending path, a straight path, a bending path, and a straight path. But that's not the only way. You could also have various kinds of frames. And here I've illustrated some frames of single bend paths that also form a C4. And if you have some frames, what would a grandfather like me do? I would put a picture of my granddaughter inside. And you can tell that this is an early result because this granddaughter happens to be 10 years old already. the structure of cycles is, in fact, well understood now. If you have a representation of a 4-cycle, there are only these ways of doing it, either as a true pi or a false pi or a frame. No other representation is possible. For larger cycles, all kinds of things can happen. You could have on the left a single bend paths that just sort of go around, looks like a circle. And here at the bottom, I put in as many little paths as I need to build Cn for any n greater than 4. I can even have things that sort of don't feel like a cycle, like this staircase going up and coming down. Well, there are probably some tall classrooms that have this kind of interweaving staircases where you have 2 staircases in the same column, and you have the up paths going this way and the down paths going that way. Maybe you've seen some buildings like that. And if you go up the up path and down the down path, you will never retrace. It really is a chordless cycle. Or you could have weird things like I have here on the right, which is also a cycle. So there's not much chance that we're going to characterize longer cycles. A C5, yes, maybe a C6, but not longer ones. What about the antiholes, the complements of chordless cycles? Well, C5 bar is the same as C5, so it's representable. And C6 bar is also representable, and here's a representation for it. On the right, I have a drawing of C6 bar. Sometimes we call it a prism, and a representation for it. And I want you to notice something in this diagram. Notice that I have single bends that 1 and 4 are sharing on this horizontal, 2 and 5 are sharing on this horizontal, 3 and 6 are sharing on this horizontal, and on the bottom, 1, 5, and 3 are sharing, and 2, 4, and 6 are sharing. I'll come back to that example in a second. Bernard Ries showed that the other antiholes, the larger ones, are not B1 EPG. It's impossible to have Cn bar for n greater than or equal to 7. You could probably work a proof out on that on your own using the characterizations that we've had so far, because Cn bar would have some 4 cycles. There are only a small number of ways of representing those 4 cycles. It's enough constraints for you to build a contradiction. And in fact, that's what his proof does. He breaks it into 3 cases, looking at true pi's, false pi's, and frames. Now, this representation is a special kind called two-side boundary generated representation. Why is it boundary generated? Because the endpoints of each path is on the boundary of this rectangle. They are anchored on the boundary. And why is it two-side? Because I'm only using 2 sides, one horizontal and one vertical. So this example, the prism, the complement of the 6-hole, is an example of a 2-side boundary generated representation. Each path has one endpoint on the x-axis and one on the y-axis. And we denote this class as 2-side boundary EPG. And there's a theorem that goes with this. A graph G admits a 2-side boundary EPG representation if and only if there exists an edge covering of the vertex set by 2 clique partitions. A clique partition will be a partition of the vertices such that each piece of the partition is a clique. I take 2 of those, and I want to be able to cover all of the edges. Well, you can see that happens in this representation. 1, 3, 5 is a clique. 2, 4, 6 is a clique, edge clique. And here on this side, I have an edge clique, edge clique, edge clique. And that will cover all of my edges in the graph. So I have the horizontal clique partition and the vertical Equivalent to that is that G is claw-free, gem-free, four-wheel-free, and odd-hole-free. Now, this notion of covering using clique partitions is equivalent to what is sometimes called the prog dimension or the product dimension of a graph. In this case, P dimension of the complement of G is equal to 2. And they're so called because they were introduced by some Prague mathematicians. And it's also equivalent to another parameter that's well known called the equivalence covering number, EQ, which was introduced first by Pierre Duché in France and then by Noga Alon in 1986 in Tel Aviv. Of course, I don't think any of them knew about the others' work, but you can see the order of who discovered them. And the forbidden subgraph characterization is due to Frédéric Manfrey and 3 other authors. But we will see more about this later. Let's look at complete bipartite graphs. Well, K33 is not B1 EPG. I suppose you could work out a proof of that also using the theorem on how C4s are represented. And K25 is also not B1 EPG. These are our minimal obstructions. Anything that has smaller parameters would put you into B1 EPG. So I'll ask the question, is K24 boundary EPG? We know that it's B1 EPG because 4 is smaller than 5. And these are minimal obstructions. But is it boundary EPG? You might ask. Well, not using 2 sides. Sorry. If I try to lay them down on 2 sides, I can put down 1 and 2 with A, but there's no room for 3. Not using 3 sides, because if I try using 3 sides, I can put in A and 1, 2, 3, but there's no room for 4. But yes, I can do it with 4 sides. And here's a representation using 4 sides. Well, I could ask about wheels. W4, the wheel 4, is B1 EPG, but the larger wheels are not, also proved by Bernard Ries. Exercise, are the 4-wheel and the 3-son 2-side boundary, or 3-side boundary, or 4-side boundary, or not boundary at all? There's the answer, but whoops, you missed it. But if you're out in cyberspace, you can go back and take a look at the answer. But try to figure out anyhow before you look at it. So one time at Dagstuhl, when Elad Cohen and Bernard Ries and I were at a workshop, we were looking for a problem to look at. And we asked, well, what would be the co-graphs that are also B1 EPG? In the course that we just had, we learned quite a bit about co-graphs. They are the P4-free graphs. And we came up with this characterization after quite a bit of work and quite a bit of coffee, that a graph is a co-graph and B1 EPG if and only if it is K33, K25, K321, and K2221 free. These are these are complete bipartite, and these are complete multipartite in the natural way. So we have a characterization of that. But you might ask, what are the co-graph boundary EPG graphs? Are there some smaller forbidden graphs? Could you reduce this? Can you give a characterization for co-graph intersected with boundary EPG? Well, I leave that as an exercise to you. I frankly never looked at it. But I guess if you give me a solution, I'll have to read your proof and see if it's right. And then I could add it to my talk, and maybe you can write a little paper. So whenever I talk about grids, I like to show this slide. Look at it very carefully. Stare at it for a while. You see anything strange happening? Looks like it's moving, right? But it's not an app. It's just your brain. Your eyes and your brain are causing this. This is called the Hermann grid. It's very famous in cognitive science. Let's talk a little bit about boundary EPG graphs and some of our main results. We are able to show that the boundary EPG graphs can be covered by two collections of vertex disjoint cobipartite chain graphs. So this is in the spirit of what we saw for two-side being covered by clique partitions. Here we're trying to cover using a different kind of gizmo, vertex disjoint cobipartite chain graphs. And this generalizes what we saw in the two-side case. We also have a tight upper bound on the equivalence covering number for general boundary EPG graphs. And we have a linear time testable characterization for boundary EPG trees, when a tree is boundary EPG. Let me go into the details a little bit. A bipartite graph is called a chain graph if for each color class, the neighborhoods of the vertices in that color class can be linearly ordered with respect to inclusion. Equivalently, it's well known in graph theory that it is a bipartite graph which is 2K2 free. That's two edges that are not at all related to each other. 2K2. Okay. So now we note that the linear orderings of the neighborhoods of the vertices of each part is still preserved when you take the complement. So a cobipartite chain graph is simply the complement of a bipartite chain graphs. And here, again, is our two-side theorem, but with a few extra lines. The following are equivalent, that it's two-side boundary EPG, if and only if it has equivalence covering number 2, this we saw, if and only if the reduced graph, that is when you get rid of twins, has product dimension 2, that this is new for us today, the line graph of it is a line graph of a bipartite multigraph. It has the forbidden subgraph characterization that we saw, and the clique graph of G, the intersection of the maximal cliques in G, is a bipartite graph. That's the result for two-side. The cobipartite covering theorem is this one. If G is boundary EPG, then G can be covered by two graphs, GH for horizontal, GV for vertical, where both of these graphs are vertex disjoint unions of bipartite chain graphs. This is only in one direction. Moreover, if G is three-sided, then the graph GV can be further restricted to be an equivalence graph, that is the disjoint union of cliques. These are necessary conditions, but they're not sufficient. And our upper bound for tightness is that if G is boundary EPG on n vertices, then the equivalence number is at most 2 log n plus 1. And further, if it's three-side, then you can knock it down to log n plus 2. Moreover, there exists n-vertex three-side boundary EPG graphs with equivalence covering number at least log n minus 1. So we're zeroing in on what the real value might be. And lastly, we're able to characterize and recognize the trees that are boundary EPG. A linear forest is a forest in which every connected component is a path, and it's a linear K-forest if it's a linear forest where every path has at most K edges, i.e., at most pk plus 1 as a chordless path. And the linear arboricity, K-arboricity, is the minimum number of linear K-forests whose union is a graph G. And notice that linear 1 arboricity of a graph is its chromatic index. This is a parameter that was introduced by Michel Habib and a student of his, Perroche. Here's an example in figure. A and B illustrate two edge disjoint linear 3 forests. That means I'm allowed to have P4s, but nothing bigger. And their union, if I were to lay them one on top of the other, would give me a tree. In the olden days, when we used to give lectures on transparencies, I would make a transparency for A. I would make a transparency for B. I would then physically take one, put it on top of the other, and you get C. But what can you do? We're in a modern age, and we can't use transparencies anymore. So I would have to write fancy PowerPoint to get those two things to like come across my screen and merge. It's a lot easier in the olden days to show that. Right. Okay. So characterizing and recognizing boundary EPG graphs. A tree is boundary EPG if and only if it can be covered by two linear 3 forests. Moreover, if it has 3-side representation, then it's if and only if we can restrict one of the forests to be a disjoint collection of edges. Well, that's very nice. And we also have an algorithm whose complexity is polynomial. It's based on using a result that gives a linear time algorithm to find the linear K-arboricity of a tree, and then we use that algorithm, modified a little bit, to recognize our boundary EPG trees. We still do not know whether one can efficiently recognize boundary EPG graphs for 4-side. Though the problem is linear, and for trees, we suspect that it might be NP-hard in general. What are some of the other computational aspects of B1 EPG? Well, in 2010, it was proven that recognizing B1 EPG itself, not boundary, is NP-complete. And that was improved 3 years later to show that even if you have a representation that requires the shape L, only one of the 4 shapes, recognizing those graphs, which is a smaller class than this, subclass, is also NP-complete. And my colleague, Gila Morgenstern, showed that max clique on B1 EPG is linear, and min coloring on B1 EPG is NP-complete. We then continued that line of research with a graduate student, Dror Epstein, and showed that the maximum stable set and also the minimum dominating set on B1 EPG are also NP-complete. And just recently, fresh off the presses, not just a couple months old, is that min coloring max stable set and min dominating set is in fact NP-complete even if you only have L bends, not all 4 different places. Now, that result is interesting in and of its own, but what really makes it nice is that it's based on a new theorem that says that for any graph G, let G prime be obtained by subdividing each edge of G with at least one new dummy vertex. You do that, then G prime is L EPG. It surprised us until we discovered it and saw the proof, and then doesn't surprise you anymore. We also studied approximation algorithms for these three problems because we proved that they were NP-complete. And in a paper that we had in 2013, we gave a 4 approximation for min color, a 4 approximation for max stable set, and an 8 approximation for min dominating set. We don't know if this is best possible, but this is the best that we could do. And I don't know, maybe some of you might be able to improve it. This, of course, requires that the representation be given, since if I just give you a graph, you wouldn't be able to recognize even at this point whether you're in the class or not. But this is typical of the kinds of problems you would receive. You would receive a representation from a VLSI designer or from your granddaughter who's now 10 years old drawing drawings for you. And you take that input and you try to color it. Or maybe she makes it and tries to give it to the 8-year-old granddaughter to see if she can color it. So they may not know a lot of graph theory, but I'll tell you, grandchildren know a lot about coloring. So back to our results. That's what we know about B1 EPG for these problems. Well, we also, of course, introduced the class BK EPG for any k, and you might ask, what about the higher numbers of bends? What is known there? And here, there's a lot of room for future research. Well, interval graphs are B0 EPG. We just saw that. It's pretty trivial. And trees are B1 EPG, and we saw proof of that. Not so trivial is planar graphs. Today, we know that planar graphs are either B3 or B4. That is, you can certainly do them in B4, and maybe you can do it in B3, but you can't. But there are examples of graphs that are not B2, and they are planar graphs. Outer planar graphs, however, are all B2 EPG. Circular arc graphs was proven just about a year and a half ago to be realized in B3 EPG. And there are a lot of open questions to do the same thing for other interesting families of graphs. Are there other interesting families where you can bound the EPG number? In general, you can, in fact, always find for any k EPG graphs that cannot be represented with only k. So it is an increasing, growing family as k gets larger and larger. But if your graph is planar, then you know that you can do it using 4 or maybe 3. And if your graph was a cograph, you could do it using, oops, I don't know the answer. You'll have to figure that out. And then you can write it in the same paper where you write the other result of the other exercise. So, in conclusion, we've presented the family of BK EPG graphs, and we studied some of the mathematical and algorithmic aspects of those B1 EPG graphs. We introduced and studied boundary-generated B1 EPG graphs and posed several open questions, but the topic remains really elusively open. We hope that it will be the source of much interest for all of you to work on in the coming years. Here are the references, and by now maybe there are a few more references, but I would hate to make the font even smaller. I've circled the ones that are our newest ones that I spoke about today. So you're encouraged to read more about intersection graphs in my 2 books that you probably know about. And I would like to thank you all for being here and listening to this talk. And I would like to thank my co-authors who are here beautifully displayed in front of you. So thank you very much for attending. Thank you very much for being here in IIT-Kharagpur. And I look forward to seeing you again some other time, tomorrow or tomorrow or tomorrow.